This is a rather theoretical exercise that has two purposes. One is to verify that the notion of convergence in probability is quite natural and that it has properties similar to the notion of convergence of sequences. And the second purpose is to get a little bit of practice with the formal definition of convergence in probability. So what is the statement saying? It says that if we have a sequence of random variables that converges to a certain number a, and this basically means that when n is large, the distribution is highly concentrated around a, and if we have another sequence of random variables that converge to a certain number b, which means that the probability distribution of yn is heavily concentrated around b, in that case, then the probability distribution of the sum of the two random variables is heavily concentrated in the vicinity of a plus b. So what are we saying? If xn is very close to a with high probability and yn is very close to b with high probability, then the sum will also be close to a plus b with high probability. This is the intuitive content of the statement. Now we want to establish this formally. Before establishing this statement, however, it will be good practice to verify a property of this type for the ordinary convergence of sequences of numbers, not random variables. So let us do that. What we want to show is that if a sequence of numbers an converges to some number a and another sequence converges to some number b, we want to show that in that case an plus bn converges to the sum of a plus b. And we want to do this formally. So let us start with the definition of convergence. What does it mean that an converges to a? It means that if I fix some positive epsilon, then there exists some number or some time such that if we consider some n bigger than n0, then an is close to a, in the sense that this difference is less than epsilon. Now, this is true for any positive epsilon. So, if instead of epsilon I take epsilon over 2, this will also be true. Eventually, after some time, we will have the property that an minus a is less than epsilon over 2. Similarly, if bn converges to b, then we will have the property that there exists some time, let's call it n0 prime, such that if n is bigger than that particular time, then bn minus b is going to be less than epsilon over 2. Okay, so after time n0 and after time n0 prime, these two inequalities will be true. So if we wait long enough so that both of these inequalities are true, that is, if n is bigger than the maximum of n0 and n0 prime, then we will have the following. We will have that an plus bn minus a minus b, which by an elementary inequality is less than or equal to an minus a plus bn minus b. Okay, where does this inequality coming from? This is a general inequality about absolute values. If I give you two numbers, the absolute value of x plus y is always less than or equal to the sum of the absolute values. So we're using this inequality where x is an minus a and y is bn minus b. So we have this inequality, but when time is big enough, an minus a is less than epsilon over 2, bn minus b is also less than epsilon over 2, and putting everything together, this is epsilon. So what have we shown? That if an converges to a and bn converges to b, so that all these relations hold, then if time n is large enough, then the difference between this number and that number is going to be less than epsilon. And this is true for every positive epsilon. But that's just the definition of convergence of this quantity to that quantity. And this is the proof of this elementary relation about convergence of numbers. Now let us turn to convergence of random variables. We fix some epsilon that's positive. In order to show convergence in probability, we want to look at this difference and look at the probability that this difference is bigger than epsilon in magnitude, and we want to show that this quantity converges to zero. If it does, then we will have established convergence in probability, because that's just the definition. Okay, now this is the event that the sum of the random variables is close to a plus b. And we want to use the fact that xn is close to a and yn is close to b. So this is the event that, let's write it in a somewhat different way. It's the probability of the event that xn minus a plus yn minus b is bigger than epsilon in magnitude. Now, for a sum of two numbers to be bigger than epsilon in magnitude, it has to be the case that either one of them is larger than epsilon over 2, or the other number is bigger in magnitude than epsilon over 2. So if this event happens, this event must also happen. This means that this event is a subset of this event. This is a smaller one. If this happens, then this one happens. So since it's a smaller event, it means that its probability is less than or equal to the probability of that event. Now we use the union bound. The probability that something happens or something else is happening is less than or equal to the sum of their probabilities. And now, since xn converges to a in probability, then by definition we know that this quantity converges to zero as n goes to infinity. Similarly, since yn converges to b in probability, this quantity converges to zero as n goes to infinity. This is a sequence of numbers that converges to zero. This is another sequence of numbers that converges to zero. Therefore, the sum of these two sequences also converges to zero. In essence, here we're applying what we established earlier about convergence of numbers. If a sequence converges to zero and another sequence converges to zero, then the sum of these sequences also converges to zero as n goes to infinity. But this is exactly what we need to show in order to establish convergence in probability of xn plus yn. We have shown that if I fix any epsilon positive, no matter how small, the probability that I'm more than epsilon away, that probability that xn plus yn is more than epsilon away from the supposed target or the limit, this probability must go to 0. And that's exactly what we established here, and this completes the derivation.